Good morning, friends. Welcome back to AI class. Good morning. Am I audible? Oh, thank you, Satish. Good morning and welcome to Artificial Intelligence class. We are in our first unit. The introduction and basic search strategies. That's what we are looking now. Once we do this, we'll go into advanced search strategies, then look of basic representation and some reasoning task. Then we complete our knowledge. When the situation is uncertain, how reasoning should work. And in fourth unit, we look at various learning techniques and finally create a expert system and see how we can work artificially. These are the objectives we need to study in this. So the objectives for studying this subject is to make sure that you know about different AI agents, you know various AI search algorithms, you know various fundamental knowledge about the representation, knowledge representation and reasoning, and then build Markov models so that you can step into applied AI. These are our outcomes. So after completing the course, you should be able to answer these questions, formulate an efficient space for a problem at hand, solve the problems by searching the problem space for appropriate solution, possess the logical concepts to represent the problem in unambiguous manner, possess the skills to represent the knowledge in more efficient way, build the expert systems through the available knowledge, include uncertainty to problem space for intelligent solutions, make machines learn human defined concepts, use artificial neural networks to simulate human thinking in problem solving, and finally teach how to process natural languages by the machines as we do. I keep repeating this every class just to make sure that this whole thing gets into deep into your mind and never forget what are we aiming at. Yeah, these are our eight goals to reach at the end of this course. Oh, there's a syllabus we are talking about. And last class we have seen uh, uninformed way of searching. That's blindly searching the search problem space. We are just left into the problem space where many states are there. There is one starting state where you are thrown in and you are asked to reach to the goal state. Don't know whether goal state exists in that space or not, but with a blindfold you are asked to move around, help yourself and make sure to reach the goal state, and if you reach the goal state then shout success, otherwise keep searching and searching and searching till you faint. Yes, that's a big drawback of the one which we talked about. If you look from the human point of view, but when it comes to machines point of view, that's the simplest thing to implement. It was possible to implement, but definitely it's not preferred when it comes to calling it intelligent one. Therefore, moving towards making it more intelligent, let us get into the next world of problem solving, which we called searching the solution heuristically. So now some optimization is implemented, and iteratively at every stage this heuristic function or a cost function will tell us are we moving in right direction or not. And if we are moving in right direction, we continue to move in that. Otherwise it is going to give an alarm saying that no, you are going in wrong direction. So if you remember your childhood, during the schools you used to play blindfolded, and somebody used to tell you go left, go right or something, just trying to make sure that you move in the right direction. So it's similar game we are talking of. So somebody whom we can trust is helping us to move left, right, up, or front, back, and all that, so that we can reach our goal. And it's up to the understanding between the one who is doing and the one who is listening. The whole story matters. So if you have better understanding, better synchronization, then easily the things can be done. So this better synchronization is what we call a better type of heuristic function has to be built, which is going to also be called a cost function, because anything goes wrong is going to cost dearly, and hence we want to work with minimum cost. So minimum cost in the sense, if you talk in terms of time, then we minimum number of steps we want to complete. If you want to talk about space, then without taking much space we need to solve our problem. Or best thing is make sure that you use minimum space and minimum time to solve the problem. So problems, this strategy solves the problem faster than the classic method. And yes, most of the time the exact solution may not be required. The solution may be approximate. So even if it is approximate solution, most of the time our problem is solved. So simple thing is, if I ask you a question, what is the value of pi? Yes, you can answer it. Somebody can say 3, somebody can say 3.1, somebody can say 3.14, somebody can say 3.1415, or even you can say 3.1415926 or if you have patience, then you can keep on telling forever, because there is no end for it. So now it all matters is how accurate the answer you are interested in. So if you are interested in only an integer, 3 is sufficient. If you are interested in one decimal place accuracy, then 3.1 is okay. If you want through two decimal places, 3.14 is okay. So that way, if you look into our classical method, and if you ask question like q the value of pi, then it keeps giving the answer. And this reminds me of one situation of a very famous what do you call TV serial of space called Star Trek. In that one intelligent scientific officer will be there who is taking care of the whole computer, which is called master computer. In that everything is oral, so he keeps telling computer what to do. The computer keeps telling back the answers and all that. So sometime this their spaceship will be moving in some region which is being affected by some particular rays, maybe alpha beta rays or gamma rays or some rays or magnetic field, which he was afraid that it may affect the computer. So not to take any chance, and he finds out that if the computer is busy working, then it may not affect the computer. So he wants a computer to be busy, but the master computer was built at so high level, high technology that any impossible question you ask within microsecond, nanosecond, it used to answer. Then he used his brain and said, "Master computer, give me the value of pi till the last digit." So you just keep typing it. So it keeps doing it and doing it and doing it. So he was 100% sure that the master computer will never complete its task. So it keeps doing it forever. And when the ship is out of that danger zone, he says, "Okay, master computer, you can stop calculating that." So that way, there are some issues. Now I think you understood the problem. Even some genie type problem was there. So you make sure that give a problem and get the answer. So if you don't want a genie to be free, then you have to give a question which should never be solved. Yeah. So if you are talking about such questions, then classical methods will never come back with any answer. But yes, we want answer as early as possible. But exact answer, if it is not possible, no problem. Approximate answer is okay. So the classical methods sometimes cannot give exact answer because they cannot reach the exact answer, but we can think of finding an approximate solution for that. And what is how is this happening is there is a trade-off between either optimality or completeness or accuracy or precision. One of them or some of them are not taken care just to make sure that we get the answer at the earliest. So either you don't go for optimality, you compromise in optimality or compromise in completeness or accuracy or precision for getting a answer at the earliest. So to produce a reasonable amount of to produce in a reasonable amount of time a solution that is good enough for the problem in question. Now, why do we require? Just to make sure that in a given reasonable amount of time we should get the solution which is sufficient for the problem at hand. And when the speed is more important than accuracy, yes, the speed is more important than the accuracy, then now what is the what you say if I ask you a question like what is today's exchange value for a dollar? Yeah, it's 73 rupees or something. Yeah, if you keep on telling more accurately, then definitely you need to search and all that. Their speed gets the problem. So we are not interested in doing a big business in with US and all that. Just as for the sake of general knowledge, I just asked a question: what is dollar rate today? So, if you say 72 or 73 or 74, it's not going to make much difference because I am not having even a single dollar, nor I am trying to purchase a dollar. So how does it matter whether it is 72, 73, 74, or 85? It doesn't make any sense. But what makes sense is how early I get the answer. Yes, that's so accuracy may not be that important when speed is important. Such cases we need to work on that. And we are going to work with heuristics when the problems are exponential in complexity. Exponential, I said, um, that is going to convert that into a polynomial complexity. Like yesterday, we were talking about 2 to the power 20 becomes 1 million, whereas 2 into 20 becomes 40. So you just compare what is 40 and what is million. So you want million or 1 megabyte of memory or 40 bytes of memory, you decide. Or are you ready to wait for 1 million seconds, or you want to answer in 40 seconds, you decide. So you get answer after 1 million seconds, but it is accurate answer. But you get a answer after 40 seconds, may not be that accurate, but yes, kaam chalega. Doesn't make any difference with your analysis, whatever you're doing. So that case, things will be done. Heuristic techniques are weak methods because they are vulnerable to combinatorial explosion. Yes, we look at it combinatorial explosion, what it means shortly. Yes, weak heuristic search algorithms have different names, different people, different books refer them as different by different names. It can be informed search, heuristic search, or heuristic control strategy, and so on. Applied if effective if applied correctly to the right types of tasks and usually demand domain specific information. So unless until you have a domain specific information, you cannot proceed with this type of techniques. And definitely it needs extra information to compute preference among the child nodes to explore and then expand. So you need to just at every time you need to compute. So extra computation is required. Indeed, this extra computation you are going to do some 40 times, and this computation is going to take some nanoseconds. Then it overall it may be doing 40 nanoseconds extra work. But if it is going to save your search time from million seconds to 40 seconds, I don't think sparing 40 nanoseconds or 400 nanoseconds or even 40 milliseconds is going to make any difference. Yes, that's where we look into. So the different types of heuristic search we can think of are called best first search, A star search, bidirectional, debut, beam search, simulated annealing, hill climbing, constraint satisfaction problems. Some of the names, different versions of heuristic search are there. Okay, let's start with the hill climbing search. Hill climbing, the name is given, assuming that you are reaching the peak of the hill. Aim is to reach the peak of the hill, so you keep climbing. And how can you climb? Many ways you can do. You can go up and down, up and down, up and down. You may never reach peak, or you may keep circling around the hill, may never reach the peak, or you keep moving up and up and up every step, and easily, early, you can reach the top. So this reminds me of what Hillary was talking in his book. Hillary was talking in his book that, excuse me. Okay, when Hillary and Tenzing were moving up the uh, Mount Everest, they were trying to reach the top of the Mount Everest. Then they were at every step they were moving up and up and up and up, and immediately they realized that there is no more step to climb up. And very lately they uh, stuck an idea that they are already on the peak. There is nothing more to climb. So that's what we are talking about. So we want to reach say a place where you don't have any more thing to climb. That's how the hill climbing strategy works. It's a variant of a generate and test algorithm. It's it's going to make use of greedy approach. So that means when you are given choice, which one you want, yes, definitely we show our greediness and we try to fetch the most costliest thing available among the things offered to us. So we go for a greedy approach and move only in the direction which optimizes the cost function for it. So we are given with many choices. So there are many types of hill climbing: a simple hill climbing, steepest ascent hill climbing, stochastic hill climbing. We'll just check that in shortly. What is a hill climbing? I think this will be a better starting point for discussion. So if we are here, say if we are here, now there are many options to move. There are many options to move. You can go this way, or you can go this way. You can go up, you can go down. Now, if you look at it, if you move this way, something happens. 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 Then assume that you are here. Then, if you move left, right, up, down, then you realize that if you move left, you are going a bit lower. If you move to the right, you are going bit higher. If you go down, it goes really down. If you move up, it goes very much up. So one step left takes you little down, one step right takes you little up, one step this direction takes too much up, one step this direction takes too much down. Now, out of all these four, which one you prefer? Definitely, you will prefer this direction because this is taking you up for a larger, higher elevation. So we prefer because our goal state is here. This is our goal state. Therefore, if you move this direction, then you will keep moving towards this as early as possible. So that way, what is it we are doing is we initiate our state wherever we are and verify are we on the goal state. If yes, then return success. Otherwise, then put yourself in a loop, look all the directions and see any of the directions is better than what you think. If yes, go there and then verify are you in the goal state. If yes, declare yourself done. Otherwise, keep doing this on and on and on till you reach your goal. So evaluate the initial state, loop until a solution is found or there is no new operators left to be applied. Select and apply a new operator. This new operator in the sense, take a left move, take a right move, take a front move, take a back move, whatever you, four moves are possible. If you are talking about a chessboard, then four moves are possible. Or if you talk about chessboard, eight moves are also possible. So look into all eight directions. Whichever direction is going to give you a better one, evaluate the new state. So try all the options. If the new state is the goal state, go there and quit. Declare you reached it. No, but it is better than the current state. Go there and then again put a loop. So you were here, then you found this point. This point was better than this point was better than this. So we are here. Then we looked at all four direction. Then we found this point, and this point was better than all other four. So we went. We looked in all four directions. Then we realized this point is better. Then we went there. Then we realized this point is better. Then this point was better. Then this point is better. And that way, till you reach the goal, you can keep doing. But as you initially said, it may get you into infinite loop or some uh, no solution path. So we'll see that shortly. So that's what the hill climbing algorithm is going to work with. So let us see how does we work with. So this is the initial state, and this is what is our final state we want to reach. Okay, what are we doing now? As we looked at last time, we said from here to three options are there. You can move tile 3 down, you can move tile 8 to the left, right, or move tile 5 to the top. So that's what we were doing in our last class. But now we are not going to do that, because tile 3 we don't move down, because tile 3 is in its correct position. Therefore, please don't disturb tile 1, tile 2, tile 3, and tile 4, because they are in correct position. Now, how many are there in wrong position? Tile 8 is in wrong position. 7 is also in right position. 8 is in wrong position. 6 is in wrong position. 5 is in wrong position. Okay. Now, how do I know? How do I quantize that? How much efforts I need to put so that I can reach the goal state. That's what I want to know. So for knowing that, let me see how many moves I have to make to reach my goal state. So how many moves are required for 5 to reach? So 1, 2. So 2 are required for 5, and for 6 it has to come here, then here. So 2 moves for 6, and 8 can just come down. So one move for 8, two moves for 5, and two moves for 6. So 2 plus 2 plus 1. 5 moves are required to reach the goal state. Now, what has happened? 3 has come down and 5 has gone up. So I think this was not required, but still we are just to show the what you say, what happens if you do wrong move. Okay, if we are doing 3 down, you can even take 8 to the right, and you can plot another one here. If you take 8 to the right, then what is happening? Now you see how many moves are required to shift. So one move for 3, as usual. 2 moves for 5, 2 moves for 6, one move for 8. So that makes 6 moves. So earlier it was 5 move, now it has makes 6 moves. That means we are not going in the favorable direction, we are going in the wrong direction. Therefore, this is not suitable answer. So the suitable answer may be some other thing. Let me see what would happen if you move 5 up. So I moved 5 up. Then after that, how many are there? So this 5 should come here. So one move is required for 5. 6 should come here. So it has to move here and then here. So two moves are required for 6 and one move for 8. So one for 5, one for 8, two for 6, 1 plus 1 plus 2. That makes total 4. So earlier it was 5, now it has become 4. That means this is more favorable situation, and hence we get into this. Now from here, what is possible? You can move 5 down, you can move 6 to the right. 5 down is going to get you back to that, therefore no point in doing that. So let me look what happens if 5 comes down, then this 4 will become 5. So there is no improvement, therefore we don't go back. So we just get further. We move 6 to the right. So after moving 6 to the right, how many misplaced things? 5 should come here, 1, 6 should come here, 2, 8 should come here, 3. So we need 3 more moves. Then what all possible? So this blank can be replaced by 6, can be replaced by 8, can be replaced by 7. If it is replaced by 7, this is how it looks like. If it is replaced by 8, this is how it looks like. And if it is replaced by 7, then this should come back 1, this should come back 2, this should come here 3, this should come here 4. So it needs 4 moves. Whereas instead of shifting 7, if you shift 8, then what is it? If you shift 8, then 5 should come here, 6 should come here. So only 2 more moves are required. Therefore, we select this. We don't select this, and we select this. And then if you are here, instead of, if you try to move shift back, then 3 is going to become 4. Definitely not an favorable situation. So we forget that. Then from here, again, 3 options open. 2 can come down, 4 can go left, 5 can go right, 5 can go left. If 5 go left, now 6 should come back. There's one more move required. If 4 goes right, then 4 should shift, 5 should shift, 6 should shift. So 3 moves required. Or if 2 comes down, then 2 should shift, 5 should 6 should shift, 3 more moves. So this is 1, 3, 3. So from 2 to 3 is not a good idea. What, where is 1, 2 to 1 is a best idea. So get to 1 and then make 6 up, or make 3 down. You can't make 5 right because you just made 5 to the left and came here. So if you make 5 right, it's going to become again 2. No point in checking that again. So we have checked this. This is going to take 2, whereas this, yes, that we have succeeded. No more moves required. So reach the goal. Now you can see how easily we can solve this problem. And if you compare the similar situation, you try to solve this problem with uninformed way, then we will have everywhere two, 2, 3, or 4 options, and then keep looking at it because we don't know are we moving towards our goal or not. We just keep blindly moving and moving and moving with the hope that somewhere we reach the goal. Yeah, that's hill climbing. Another problem for hill climbing. Yes, this way we can continue. So there are 4 options in the first state. Then this was 3, this is 4, this is 4, this is 5, this is 5. Then this 4, this made 4, this is 6 increased. So 4, we made only one change. Then this is again 4. Then this is a 4. This is what our goal state was. So we can stop here. So there are some limitations of hill climbing. Like you may reach a shoulder, you may reach a local maximum, or our aim is to make sure to reach the global solution, whereas we may reach a local solution. So we are moving up and up. So if we are here, we keep moving up and up and up and up. And when we reach this point, and if you try to continue further, this you keep going down. Or if you go back, you still keep going down. Then you think that you are on the peak. But in reality, the peak is here, but you have started climbing from here. Therefore, you never gone this side because it is taking you downhill, and we are greedy. Therefore, we prefer only move uphill. We want more and more profit. We never bother that if we try to solve this problem, we would be getting much more profit. But we were here trying to solve this problem, and therefore we could keep moving, marching to this end so that we make highest profit possible. And later we realize that this should be the one which we go. But most of the time we will not be able to realize that we have missed the global, we have reached some local solution. Or sometime you reach a shoulder. So once you reach here, what will happen? So you keep increasing, and then once you reach this, then you try to move further. Then you realize that you, even if you move further, you are no more making any improvement. Then you realize that you may be on the top, therefore you may stop here. And that way, or because you are not able to make improvement, you try another path that will not help you, therefore try another path that will not help you. Keep looking in all directions, and all directions keep telling you that there is no improvement possible. Therefore, either you may stop, or you may end up searching and searching and searching all around. But if we had taken a dare step and said, let me continue a few more steps and then look at it, then if you had taken a bold step and moved further, then you would have seen another uphill, and then you could have continued and you reached the goal. No, same problem is with this fixed local maximum. So it looks like uh, reaching the goal state. So if you are here and you try to take a bold step, then you can continue. But here, if you try to take bold step, you may get down and get into another valley. So basically, 3 types of problems we have. One we call local solution. That's what we talked about. Other one we call plateaus. That's something to do with the plain. And then another one is ridge. So that's an example for a local search. So if you look for a, if you start from here, then you will climb this way. Because if you are here, If you are here, then move to the what do you say, west, you are going down. Move to the east, you are doing a little uh, elevation. If you move to north, a lot of elevation is there. If you move to south, you are going downhill. Therefore you prefer to move north. As you move towards north and north, later when you come here, you think that moving to east would be better. Then you come east. Then once you come here, then you again prefer to go to the north, and then you reach this point. And after reaching this point, you move to the north, you go down, you move to the east, you go down, you move to the west, you go down, you move to the south, you go down. So look all the eight directions and you realize that you are going down. So you can say that, yes, I won the battle and reached the goal. But in reality, it's not so, because the real winning post is here, not here. The mathematically what we call is the problem is not fully complex. There is some concavity in between. So if you look at our previous thing, this whole thing is convex. You don't find any concavity here. Everything is convex. So if the problem is convex, mathematically, if you call it convex, then you are sure to reach the global solution. But if there are some concavity, as you find here, there is a concave here. This is what we call convex, and this is what we call concave. So if there is concavity, that means there is possibility of local solutions. So the whole region should be convex. No, it is not. Whole region is not convex. This is convex. This is convex. There is concavity here. So this concavity will not allow you to cross it and reach another convex region. So the other convex region may be having a global solution. Yeah, that's the problem. That's what we call a local solution. We can held up here for a local solution, or you can talk about a plateau. So you are here and you move this way. This way doesn't make any sense, or it can be a ridge. Ridge is something like this. Uh, so the problem with this is, if we are working in the four directions, east, west, north, south, then you be anywhere here, you be anywhere here. Move to the north, it goes downhill. Move to the south, it goes downhill. Move to the east, you go downhill. Move to the west, you go downhill. But actual uphill is there in the northeast direction. This is north, this is east. So if we are allowed to go into northeast direction, you would have gone and reached the goal. So that means if you are allowed to travel in all eight directions, then you would have tried this also. But you are limited to, because you are talking about a chessboard like thing and you are working with, or yet a puzzle problem like, then you are limited to move x and y directions only. You are not allowed to move diagonally. Therefore you can either move your tile up, down, left, right. In all four possibilities, you are saying that it's not going to improve. Therefore you think that this is the best solution, but in reality this is the best solution. So that's a problem when we come across with ridge. So there are some, these are the drawbacks we are talking about. So how to overcome this? One is stochastic hill climbing. Don't just work with one starting point. So just start one point, consider one point randomly. So it may be here. Then apply hill climbing, you reach here. Okay, forget that. Then do one more trial. So the next trial, you may reach here. And then if you apply hill climbing, it may get you here. Do one more trial, and this trial, your sample point may start here. Then if you apply hill climbing, yes, it is going to take you to the goal. So instead of working with one solution, try to search multiple solutions. Then there is possibility that one of them will reach the steepest uphill. Then you can apply first choice climbing. So don't look all the possibilities. So randomly select one, and if it is found better, continue. Or random restart hill climbing. So that's what we just discussed. Okay, then other option would be to look for the best first search. Now what has happened is we were looking for some optimality in doing our search activity, and here we have someone to help us, though may not be exactly knowing what the solution is, but maybe giving you a rough idea what way to go. So if you're traveling and if you reach a junction point, then you are confused to select which of the three outlets to take. So if you find someone standing there, you just ask them which way to proceed to reach this point. If that fellow has 100% surety of the path and all that, then he will definitely tell exactly what to do. So that's almost not a possible thing every time. So it's probabilistically not a correct one. So there is chance that he may tell roughly most of the people who travel to that place will take this path. That's what he may tell. So probabilistically he will tell. So in last day, last few days when I was here, some 100 people has asked, and some 20 people went this way, some 20 people went that way, other for 60 people went this way, something like that he may tell. So that will give you a rough guidance what to do, and then you continue with that. So though you are not getting a perfect answer for what you are looking for, but at least you get some rough estimation about what is ahead of you. So that's what we call a heuristic way of working. So when you're working on any graph, so you place one node in an open list. If the open list is empty, then stop and run failure. Remove the node n from the open list which has the lowest value of h. That means whichever says this is the shortest path. So select that and say that you take up that path. Then proceed further. Then from there, where do you reach? Find out. So from here, if I move, I can reach this goal, this place, this place. So just look at it, what all places you can reach, and then put all of them in the list, and then continue. So how is it done? Best first. So this is a problem we are looking at. This is our source, and this is the goal we want to reach. Yes is the source, I is the goal. So we started from the source. Yes, and we have written all the nodes. And to start with, we have traveled zero distance. So we are, this all things are blank. So then we go to A because A is 3 units away, B is 6 units away, and C is 5 units away. Therefore, A appears to be a better choice. We'll go to A. So we add A to our list, saying that A we have visited. After A, this is 9 units, this is 8 units, whereas this is 5 units, this is 6 units. So we are left with 5, 6, 8, 9, and out of this, 5 appears to be more attractive. Therefore, we continue to C. That is taking 5. So A and C we have visited. After that, we have 6, 8, 9 are the three things which are further possible, from which 6 appears to be better. So we add the 6 to it. Then that is from yes, everything is done. Now start from the first node, that is A. From A, where all you can go? You can go to D, you can go to E. So add E because E is 8 units away. So add E, and then D is 9. So who is next? Next is C. So from C, look what are things you can do. From C, there is a 7, and 7 is better than 8 and 9. Therefore, add that to it. So this we have added, and 7 gets added to that. So H will come in. Now you have worked with D, then work with you have worked with C. Next, work with what is there in next? Next, work with B. Anything after B, 12 and 14 makes no sense because still 8 and 9 have not been used. Therefore, continue now with E. E, what is there? Nothing is there after E, so we don't have anything to add. Then look from D. From D, nothing to add. Then look from H. What is there from H? From H, I can go to I can go to J. So we will go to, no, from H, we can go to I. From H, we can go to I, and we can go to J. And then you come to what is there? G. G we have added. No. Then go to I, and that's it. So we found I is our goal state. So where did you come from? To I, we have come from H. From H we have come from C. C we have come from S. So the parent of I is H, and parent of H is C, and parent of C is S. That's how we read. So parent of I is H, parent of H is C, parent of C is S. So S to C, C to H, H to I is the path we have to take to reach the goal. Now we do our searching. The greedy time complexity of this space search is again B to the power M. Space complexity is also b to the power m, and it is not a complete one because uh, it may get into incomplete indefinite loop. Therefore it is not a what do you say, complete algorithm, though the state space is finite. And optimal, yes, it is not optimal. Why? We check when we look for other things. So there's another one. So this is the tree structure we have, and here we have information gathered from somebody. So how far the goal state is? Goal state is G. How far goal state is? Somebody was asked at A, he says 12. How far from B? Somebody was asked at B, how far is G? They said 4. From C, somebody asked how far it is. They said it is 7. From D, somebody asked how far it is. They said 3. They were not aware of where G is, but somehow they said 3. And after D, there is no way to go to G. That is different issue. Yes, these are all this is what we call approximate uh, possibilities. So this is what were collected from the people at various junctions and say we are standing here. How far is I? How far is J? If we are standing here, how far is E? How far is F? How far is H? How far is I? And all that we keep asking. We collected, and finally these are the answers we have selected. So we start from yes. From yes, we can go to A or you can go to B. A is 12 units. A says it is 12 units, and B says 4 units. So definitely, it makes sense that if you go to B, you may reach G earlier. Therefore, we get to B. And once we come to B, we see should we go to E or F? Then look what is E. E is saying 8, E is saying 2. therefore it makes go to F. So we go to F. And once we are at F, you just check where all you can go. You can go to I, you can go to J. I says it is 9 and G says it is 0. So definitely G makes sense. So we jump to G and we reached our goal. So from S to B, B to F, F to G is the path we have to take to reach here. Heuristically, we have used this heuristics. That means some way we have identified how far we are from the goal state. So the advantage, if you look at it, what are we doing? What exactly we did? Uh, Looking like a depth first search. Yes, it does look like depth first search, but if it is depth first search, it should have gone to the left child first and all that. But it is going this child all the time, right child. So is it that you are talking about right child depth first search? I don't think so, because if the goal state was here, then it would have come here and then here. It wouldn't have gone like this. Okay, that's what that's what we call that. It is switches between breadth first and depth first, wherever whichever gives advantages. Breadth first gives advantages, uses that. Depth first gives advantages, it uses that at every step. Not that in the beginning of the what you say solution itself you decide you're going by BFS or DFS. No, it is not that. We are ready to use any one of them, and as and when required we are ready to switch from this to this or this to this, whichever helps us better. So he is more efficient than any either BFS or DFS independently. A disadvantage, it behaves unguided at first. In worst case scenario, sometimes it behaves like an unguided. So some situations, not always. So like DFS, it may get stuck into the loop if you're talking about a graph, and definitely it is not an optimal one because you are believing in some heuristics. So you are not believing in the exacts, you are believing in heuristics, therefore there is a problem. So how to solve this problem is you can work with another one which we call A star algorithm. Okay, just revamp whatever we understood now. Use an evaluation function to decide which adjacent is most promising and then explore. At every step, find out which one is most promising. Go, using breadth first is more promising or depth first is more promising. Select accordingly and explore. And we can use priority queue to store the costs of the node. That means the cost of each node. What do you mean by cost now? The cost is this. So put them in order. That means F is put in the beginning, then B, then H, then F first, then D, then B, then H. So that way the things are put in order so that the smallest is selected first. So that way, if you start, so look from yes, A and B, who comes first? A comes first or B comes first? So definitely B will come first because B is 4, A is 12. So A is somewhere in the bottom, B is in the top. So you keep searching from the top, you find B first, therefore select B. Then from B, you try selecting E or F. Then if you look at it, E is below F because F is 2, E is 8. So you are having a queue which is prioritized. That means the one who is having a small value is given chance first to stand in the queue. It's like your school days when you are put in a queue. The shortest person will be standing in the front. The longest, highest person will be standing in the back, so that the teacher who is standing in front of the queue should be able to view each one of you. So that's what you call priority queue. They are you are not put in roll number wise. There is some priority that is neither you are put randomly, so you are put in some priority like height. So the shortest person is in the front and the longest person in the back, so that everyone is easily visible from one side. That's a priority queue. So if you work on that, then these things works better. The performance is n log n because in the worst case, we may have to visit all n nodes before we reach the goal. So we can travel all n nodes, and while traveling, we need to use a priority queue because we don't want to just make up and down, move front and back, and then identify which is shorter every time. So the best thing is once you sort them in order and then start working who comes first and all that. So therefore, priority queue should be prepared first. For that, it takes order of log n time for adding and removing any anything from the priority queue. It takes order of log n. So you need to add or remove in the priority queue each time you are moving from one node to other node. So at most you need to do all n node visits, and each visit is going to cost you log n time. Then it's going to be worst case n into log n for each activity, and you are doing it n times. So n log n is the what you say performance, search performance of time complexity. And the performance of the algorithm depends on how well the cost or evaluation function is defined designed. So still we are not clear how the evaluation function is designed, and the so the main key in finalizing what would be the performance of that particular thing. So that's it. We have seen two things. One, hill climbing. In the hill climbing, you may keep making rounds, or because if you are thinking that you are on a plane, and jumping further may help you. So something like shoulder. If you feel that if you are on the peak and if you feel that you are on the shoulder, you try to jump and all that, then uh, what would happen? You can keep moving around all the time. So that's one big problem we have is you select one point, and if it doesn't make any sense, no change, then you, if you by mistake confuse that it may be a shoulder or something, then if you think that if I continue for some more time I may get a uphill, then you keep making that round, then you may keep doing round and round and round around this. If something goes wrong in your algorithm, then that is possible. That's what it said. Some cases it may uh, take indefinite time, so may never reach the solution most sometime, or may reach local solution instead of global solution, may end up on the plateau, or may end up on some uh, local solution because of this ridge. So these are the problems with hill climbing. How to overcome? You can think of random for a restart. So whenever you get a solution, leave that. Remember the solution. Restart again randomly some other place. So do it some number of times and select the best solution you have found out till then, and continue with that. The first choice climbing implements the above one by generating successors randomly. So you just wherever you are, randomly select some 4 points all around you and select which one is giving best solution. Continue that side, and that way. Then we have problems with best first search. We have problems with hill climbing. Both these problems can be solved taking this new algorithm, which is called A star. We take up this in our next class. Okay, till then, take care. Bye. Yeah, you need attendance, so please wait for it. Attendance sheet is on the way. You have 2 minutes time for that. So make sure to give attendance and continue. Okay, thank you. Bye.